I welcome you all for this lecture series on deep learning. In this lecture, we'll discuss about the topic Introduction to Deep Neural Networks. We'll see one by one. First, Introduction to Deep Neural Networks. This deep neural networks, we are often called it as DNN. DNN represents deep neural networks. These deep neural networks are inspired by the structure of the human brain. This we have seen it in the artificial intelligence and machine learning subjects deeply. A deep neural network draw their inspiration from the way the human brain process information. Just like the brain consists of interconnected neurons that transmit signals, deep neural networks have artificial neurons that transmits values through weighted connections. This biological analogy has motivated the development of complex neural architectures capable of learning from data. They consist of multiple hidden layers and each with the neurons. The neurons, we are calling it as the nodes. A deep neural networks is composed of several layers, an input layer, output layer, multiple hidden layers, and an output layer. Each hidden layer contains many neurons or input nodes, and the depth number of hidden layers allows the network to learn abstract patterns in data. And information moves deeper into the network, it is transformed in increasingly complex ways. Next, weights represents the strength of the connections. Positive weight excites the neuron. Positive weight excitation, that we can call it as excites next neuron. Each connection between two neurons is assigned a weight, which indicates how strong the influence of one neuron is on another. If the weight is positive, weight value is positive, the activation of the previous neuron will stimulate the next two neuron, amplifying the signal through the next layer. Next, the weight value is negative, that means it suppresses the next neuron. On the other hand, if the weight is negative, it means the activation of the previous neuron will inhibit or reduce the signal reaching the next neuron. This mechanism allows the network to perform both amplification and suppression of signals to model complex relationship. Next, DNNs can learn complex functions through layer-wise computations. How it will happen means by stacking layers, each with nonlinear transformations, DNN's deep neural networks can learn to approximate highly complex mathematical functions. Each layer captures the different levels of abstraction, enabling the model to recognize patterns such as edges, shapes, and objects in data like images or speech. Next, feed forward network. This we are calling it as FFNN. FFNN means feed forward network. First, we will see the overview. The simplest type of deep network has been explained by the feed forward neural network is the most fundamental and straightforward neural architecture. It serves as the foundation for more advanced models. The simplicity of FFNN makes them an ideal starting point for understanding how data flows and how neural networks are trained. Next, data flows in one direction, that is input to hidden layer and then hidden layer to the output. In a feed-forward neural network, data moves strictly in a forward direction from input layer through hidden layer and finally to output layer. There are no feedback loops, feed-forward I am talking about, making the structure easy to analyze and train using standard gradient descent method. And no cycle loops are unlike recurrent neural networks, feed forward neural network do not revisit previous layers. It will go only input layer to hidden layer to output layer. It will not come back, the go back, feedback, and or steps. There are no cycles, which means they are stateless or cannot retain memory of previous inputs. This makes them suitable for static input data like images, but not ideal for sequences or time dependent data, real time data. Next, ideal for classification and regression tasks. Feed-forward neural networks are widely used in machine learning for tasks such as classification. Classification means if the mail we are having the spam detection, spam or not, regression, pricing, predicting the house prices. The straightforward design allows them to be applied to a broad range of problems. Next, we'll see the single layer perceptron. That means the computation. Here, single layer means only one input. This is the input layer. This layer is the input. This is only one hidden layer, and this is the output. And here the equation for this neural network is given by neurons summation is wi. Each input is x. Suppose x1, x2, x3. Each input is associated with what? Each input is associated with the weight value x1, x2, and x3, etc. And this each weight value input is associated with weight value, and additionally we'll have bias values for the fine tuning. So WIXI, if we have n number of neurons or I number of neurons, we'll write it as WIXI plus B. So each neuron computes the weighted sum of inputs. The equation Z is equal to summation I is equal to 1 to n WIXI plus B captures this, where XI is the input features. You know that this is the input features, and wi, this represents the weight values. Each input is the associated with the weight value, and b is the bias. This b represents what? Bias. This summation is the core computation that the neuron performs before applying an activation function. Apply activation function A is equal to any activation function. Depending on the application, we can use it. F of Z. After computing the weighted sum, this value, once if we are finding out, we are going to apply it in the activation function. This function may be anything. Different types of application using different types of activation function. The neuron applies the activation function f of z to determine the output A. This function introduces the nonlinearity and decides whether the neuron should be fired based on the z value. For example, if I am taking there is a threshold function, the activation function like this, the z value, if I am finding the z value, this z value is greater than 0, this output value is equal to, output value may be 1. If z value is less than 0, less than or equal to 0, the output value is minus 1. So in this way we have given the activation function. A simple activation function is the threshold or step function. This we can call it as the threshold function or a step function, which outputs 1 when if the sum is z is greater than 0, minus 1 if not. This binary decision rule makes it suitable for basic classification tasks such as distinguishing between two classes, either on or off, like that. Next one is the multi-layer perceptron. So more than one hidden layers, if it is there, we can call it as the multi-layer perceptron. Multi-layer, training uses here, the training uses the gradient descent and back propagation, and multi-layer network requires a way to adjust weights in all layers. This is done here. All layers weight should be updated if you are not getting the targeted value. This is done using back propagation, a technique that calculates the gradient of loss function with respect to each weight. And it combined with the gradient descent. Here wij, this is the new weight. T plus 1 means the new weight, and this is old weight, and this is eta into dou e by dou wij, and it enables the network to minimize the prediction error over time. Error at output is calculated. The training process begins by calculating the error between the actual output target value and the network prediction. This error is used to evaluate how far of the prediction is or how the weight should change to improve accuracy. Next, weights are updated here. The weights are updated layer by layer, first layer, second layer, third layer, etc. Using the back propagation, the error is propagated backward from the output layer to the input. Each layer adjusts its weight based on its contribution to the overall error using the chain rule of calculation. This we can call it as the chain rule. Wij t plus 1. This is the new weight, and old weight minus eta and dou e by dou wj. The weight update rule follows gradient descent, where eta is this eta, what we have seen, this eta is the learning rate. 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 This eta is the le it has the learning rate, and the dou E by dou Wij is this is the partial derivative of the loss with respect to weight. This rule ensures that the weights are modified in the direction that reduces the error. Next, delta rule and learning. Del W is equal to eta into y minus y cap into x. The delta rule is a specific case of gradient descent used in simple neural networks. It adjusts the weight by taking product of learning rate and the error y minus y gap and x input x. This rule helps the neuron learn from mistakes it makes during predictions and used to minimize error between actual and predicted output. By updating weights using the delta rule, the network progressively reduces the gap between this is the predicted, and this is the actual. Actually, we have to get the zero. In this case, zero. If it is equal, so if it is achieving, the targeted is achieving the actual one. Error is applied output neurons. Error is propagated backward here. The delta rule is directly applied to the output neuron, and then the error is propagated backward to earlier layers. This process ensures that all weights, even in hidden layers, are adjusted to improve the final predictions. Next, importance of activation functions. We have seen in the previous lectures various activation functions are there. Based on the applications, we are going to choose it. And it introduces the non-linearity into the model, and means activation functions are critical because they allow neural network to model complex non-linear relationship. Without them, the neural network would behave like a linear model, no matter how many layers it has. Without activation, we can write it as W1x plus B1 Z2 is equal to W2 Z1 plus B2. This is linear function. And the final expressions, we can write it as Z2 is equal to W2 W1x plus W2 B1 and plus B2. If you stack two layers without applying activation function, the result is still in a linear transformation. This is because the composition of two linear functions is another linear. Composition of two linear function is the another function is the linear function. This limits the model's capacity. And the final expression would be given by Z2 equal to W2 W1x plus W2 B1 plus B2. This mathematical form shows that the entire network collapses into a single linear network which cannot capture nonlinear patterns in the data. And with the activation function f of x, activation function may be anything. If you want to learn the activation function in detail, kindly check the um, artificial intelligence and machine learning other subject videos. And the nonlinear transformation, when an activation function like ReLU, here activation functions, so many activation functions we have seen, or a sigmoidal, these and all will be used for the nonlinear functions. Sigmoid is used, it adds non-linearity, enabling the network to represent a much wider variety of functions and decision boundaries. The common activation functions, mainly we are using many applications, sigmoid, tanh, and ReLU function. The sigmoidal function is 1 divided by 1 plus e power z. This z is equal to what? Weighted summation I is equal to maybe 1 to n xi wi plus bi. So this, after finding this value we are going to substitute and we will be finding out the value. The sigmoid function maps any real valued number into range 0, 1. It is useful for binary classification problems where the output probabilities are needed. However, it suffers from vanishing gradient. The main drawback of this sigmoidal function is it suffers from the vanishing gradient gradients for larger input values, and tan h is given by tan h of z is equal to e power z, the weighted sum e power z minus e power minus z divided by e power z plus e power minus z. The hyperbolic tangent function maps the value between minus 1 comma 1 and providing stronger gradient than sigmoid in many cases. It's a symmetric around 0, which often improves convergence in training. The next is ReLU function. Many functions are there. Here I have given only 3 functions. I have taken only 3 for understanding. F of z is equal to maximum of z. So here, if the value is there, maximum value it will be taking, the negative values it will omit. The rectified linear, ReLU means what? This ReLU represents the rectified. linear units. Linear units, ReLU. We can call it as ReLU. ReLU, ReLU. ReLU outputs the input directly if it's positive. Otherwise, if it is positive, it will give us the output. Otherwise, your output is zero. It is currently the most widely used activation function in deep learning because in its it is simple and helps mitigate the vanishing gradient problem and adds capacity and larger and learning power to the network. These activation functions, what it will do is these activation functions enable networks to learn highly nonlinear and abstract representation of input data and essential for solving real world problems. Next, role of nonlinearity. And the linear combinations cannot learn complex patterns. If the neural network only performed linear operations, it would not be able to model problems where the relationship between input and output is nonlinear, like classifying spirals or XOR data. And nonlinear functions allow the network to learn curved decisions boundaries. By using activation functions, the network gains the ability to learn and draw nonlinear decision boundaries, and this helps in capturing patterns that lie on curves, circles, or other complex surfaces. And each layer adds complexity by stacking the transformation f to the power l, f2, f1 of x, like that. The depth of the network allows it to perform many transformation in sequence. Each layer processes the output of the previous one, creating a hierarchical feature extractor that can learn complex functions step by step. Next, feed forward strategy or and weight vector. Each neuron takes a weighted input z is equal to w bar x bar plus b. A neuron receives multiple inputs and combines them using a dot product w bar x bar plus w vector x vector plus b. And here the result plus a bias term is the value z that gets passed through the activation function and applies the activation. A is equal to f of z. Vectorize the neuron, then transforms z into its output using activation function. This step is essential to determine whether the neuron is activated and how much influences it passes to the next layer. Next, vectorized form is given by A vector is equal to f of w x vector plus b vector. When working with multiple neurons in layer, this operation can be written in a vectorized format. This enables the model to compute many activations at once, leveraging matrix multiplication, like that. Will have matrices for faster computation and enables the parallel computation for fast training. Vectorization allows deep learning frameworks to utilize GPUs and parallel processing efficiently, drastically speeding up training and inference times. Next, applications of feed-forward neural networks and used in handwritten. This is used in handwritten digit recognition and MNIST data sets. From datasets like MNIST, even without convolution layer, they can learn to distinguish number of numbers based on pixel patterns. Next, email spam detection. F1 feed forward neural network can classify emails as spam or not based on features like keyboard frequency, sender information, and message formatting. This application demonstrates FFN NN, that is feed forward neural networks, are used in text based classification tasks. Next, basic NLP tasks, text classification. In natural language processing, we can call it as NLP. And the feed forward neural network can be used to classify sentiment, or that means a positive or negative, detect topics, or perform simple language identification using vectorized input representation like bag of words or embedding. Image classifications before CNN, convolution neural networks. Before the rise of convolution neural networks, feed forward networks were used for basic image classifications. Although not ideal for spatial data, they provided early success in computer vision tasks. And the feed forward networks are the foundation for deep architectures like CNN and RNN, radial based neural networks. Feed forward network form the conceptual and architectural base for more complex models. Understanding feed-forward neural networks is important be- before moving on to advanced deep learning models like CNN. The CNN is mainly used for the image classification, and RNN is used for the sequences. We can call it as sequences. So these are all the applications of feed forward neural networks. Hope everyone understood about the basic concepts of introduction to deep neural networks. The remaining things we'll discuss in the next lecture. Thank you.